Alright, so today this video will be for Honors Geometry 3rd and 4th hour. I will be going over the 1.A.2 warm-up first and then going over the 1.A.2 notes. And then after that you should have some time to work on the 1.A.2 homework that is in the homework packet that will be due for tomorrow. So I'm going to have the sub pause this video in just a second so that you can start working on the 1.A.2 warm-up first for about 5 minutes. After all of this is completed, A through J, there's only a front sides to this, I'll have the sub play the video again so that you can check your answers, make sure if you have any questions on this, just kind of star it or circle it, and tomorrow we'll go through any of those questions for you. So after we're done with this warm-up, then I'll move on to the notes and go through that as well. Okay, so let's start with pausing the video right now so that we can go over this in a couple minutes. Okay, so here are the answers I'm going to go through. It says give another name for segment JL. So if this is talking about segment JL, the only other way you could write it would be with an LJ with that bar on top with no arrows. That would be the same exact segment because you don't want to talk about any other segment here. It says name 4 rays with endpoint J. So we can go, endpoint would mean you got to start with your J. You can go up, down, left, right, pretty much in in any of these directions. So 4 rays here, we'll do JQ with the ray pointing to the right. You have JK. We have JN, JM. Because if you look at each of these, JN, JM, JQ, JK, and JP. And I think there's one more, JL. I'm writing all of them, but of course you only need 4. So pick any 4 of these, and you should be good. Alright, name 2 pairs of opposite rays. Now, specifically, opposite rays have to form a straight line and have to share the same endpoint. So there's a couple of them here. You could do JN and JM. You could do JQ and JP, or JK and JL. But you could pick any 2 pairs. I'll write them all down though. JN and JK. I'm sorry, JM. I wrote the wrong letter there. And then JK and JL. And then finally, the last one was JQ and JP. Okay, the next question, are points J, K, and L collinear? J, K, and L are definitely collinear because they are sitting on a straight line. You can, if they are on that straight line, they are collinear. Now 2 points, remember, are always collinear, but when you're dealing with 3 or more, then you have to check to see if they're actually on a straight line. Alright, the next one, are the points J, K, and L coplanar? Now, coplanar questions get to be a little more tricky. The question is not asking about, is it on a particular plane? It's just saying that if these 3 points happen to be non-collinear points, then remember that there's a postulate that says for any 3 points that are non-collinear, there has to exist exactly one plane. So that would make them coplanar. So let's see, where are J, K, and L? But we just said that they were collinear in this last part. So then this means that they can, for letter E here, I'm sorry, generally because they're non-collinear, you would say that, because they're collinear, you would say no, but specifically in this example here, they are sitting in plane R. So we would say yes. So that one hopefully is easy to see. Now if these 3 points were not inside this plane specifically, but they were sitting outside somewhere as on a straight line, then no, you would say they're not collinear, coplanar because they're not collinear. So look carefully at not just if your points are collinear or not, but whether they're already sitting in a plane in the drawing. Alright, so the next one here is, are points Q, J, and L coplanar? So here's Q, J, and L. Now notice these are not 3 non-collinear points, and so although they're not sitting on plane S, they're all not on plane S, and they're all not on plane R, we don't need it to be on an existing plane. We know that there exists a plane that would include these 3 points. Alright, so this would be yes. I'm going to go ahead and just write, because of that postulate that we've talked about so many times now, about 3 non-collinear points will always make a unique plane, or exactly one plane. Alright, letter G. Name a point that is not coplanar with points M, N, and P. So here's M, N, and P is not on. So if you're looking at the plane that it's on, we're talking about this plane here. M, N, and P are all on plane S. So, but we're saying not coplanar. So we need to pick a point that's not on plane S. So you could pick point K or point L. But if you picked point Q, for example, that is on plane S, and then all four of those would be in the same plane, therefore it would be coplanar. All right, name the intersection of, actually I was supposed to fill these in for you guys first, and I forgot to do that. So you weren't able to do questions H, I, and J until those are filled in. So QP and KL is what we're looking for the intersection for. That was the first one, and then you want to do QP and plane S, and then KL, and these two are rays. I forgot to mention, or I'm sorry, these two were lines. So we're talking about lines, and KL is also a line. So, and KL here is also a line. Okay, so these are all lines, and then this one was plane S. Okay, now intersections are harder to do, and so we'll go through this kind of step by step here. So QP, line QP, we want to find line QP in our drawing. It can kind of help to even like use color pencils or a pen or something to kind of outline and say, what am I looking for? Here's QP, and the line kind of keeps going. Here's the plane. So when you're saying what is the intersection between those two, it would have to be a point, because this line here is going through, I'm sorry, I did this one wrong. It's QP and line KL, which is going to be this point. So this one hopefully was easy to see. Just like in algebra, when you have two lines that intersect at one point, that point right there is the intersection. So that point was J. So point J is your intersection. Now on to the next few that get a little bit more challenging because of the planes. This time I have my plane S and line QP. And so what happens is this line and this plane, because this line is on the plane the entire time, the intersection will just be that entire line, line QP. All right, then on to this last one, KL though, if you notice, it's hard to see now because I've kind of drawn through it, but let me show you a blank copy real quick. If you look at this blank copy and you notice these little dashes, the dashed lines show that the line is going just through the plane. It's not sitting on the plane. So line KL here is sitting on plane R. It's not in plane S. It's going through plane S and hitting it at point J, kind of going right through it. Okay, so that's kind of the idea. So when we're looking at the intersection between plane S and line KL, there's going to be just one point where their intersection is, which is point J. So intersections can be tricky. We'll go through more examples like these if you had some trouble with this. But since you didn't know what the blanks were, we'll go through a lot more examples that you can try out as well. All right, so now let's go ahead and move to our notes. Everyone go ahead and pull out your 1A2 notes packet, and we'll start there. All right, so 1A2 notes today, it deals with identifying points, lines, and planes a little bit more. We've already kind of been doing that as it is, but we're going to do more with intersections today. So that warm-up that you just did was kind of a lead-in into where we're going right now. So first of all, before we get to the actual examples, here's a quick definition of an intersection. We did intersections in Algebra 1 with just lines mostly. You did two lines, and you would say, are they do they infinitely cross? Are there infinitely many solutions? Are there no solutions, or do they cross once? And that's kind of similar to how we do in geometry, but we'll now look at planes, which makes it a little more challenging. So it's the intersection of two or more geometric figures if they have one or more points in common. Or I'm sorry, two or more geometric figures intersect if they have one or more points in common. Okay, so the different types of geometric figures that we deal with, sorry, let me zoom out for a second. So the different geometric figures that we deal with and look for those intersections with are a point, right, a line, and a plane. All right, so we're going to do some examples now, and we're going to try to consider the different intersections between like a point and a line, and a point and a plane, and so on. Just all the different, a point and a point, etc. We'll do all the different kind of different ways of looking at those. It says how many, and here's what we're going to try to answer. How many ways do the figures intersect? And it could be once, it could be infinitely many times if it's happening all the time, or it could be none, because that's a possibility too. No solutions is fine too. But let's see here. Then we're also going to, it says what are the geometric figures do the intersections represent? And so what happens is, say it's infinitely many times, that means a line would have to be on top of another line. Or if it does cross just one time, it would, we'll kind of talk about what the geometric figure looks like at that point. All right, then we're going to draw all the possible intersections. That's going to be kind of the hardest part, to kind of do these sketches, including labels, so that because it'll tell us like what we're talking about here, points and lines. This is what homework will kind of look like too, and the best way to practice with this is, of course, just doing as many sketches as you can. All right, so here's our first example. We have a point M, and it's on line J, and we're looking for the intersection. So if I was to kind of draw this, I know I like to go to drawing kind of first sometimes. So here's my line, J, and pick a point on the line and call it M. That's pretty much the best way to imagine a point and a line. And so how many ways do the figures intersect? Just one way, one time. Specifically, it's going to be, and the geometric figure that the intersection represents is a point. They intersect at a point. All right, so that's kind of that we labeled it. Here's our drawing. Here's how many times they intersect, one time, and at what geometric figure. All right, let's try another one, line J and line K. So two lines are intersecting. Then there's a lot of different ways we can kind of imagine this. You could think about it back from Algebra 1, where you could possibly have a no solution. You could have an infinitely many solution, but we're going to go ahead and just do the one solution because that's the most common way of thinking about it. J and K are the two lines here, and so they'll meet at a point. So again, I'll write 1 point. Now, in parentheses, I'll go ahead and still write infinitely many solutions. Oh, infinitely many or no solution is possible. Because the lines could be parallel if they never cross, or if it's a line sitting on top of another line, which is when they're coinciding, then that would be an example of infinitely many. All right, so that would be a line and a line. So far, hopefully the first two examples, not too bad. But let's move on to planes, and that's where it gets a little bit more trickier. So a line and a plane, there's two ways that a line and a plane can intersect. And so one way would be to have a plane. So I'm going to draw it as well. Here's my plane, P. I labeled my plane. And then I'm going to draw it so that it doesn't actually go, it's going to just kind of start, the line is going to start, and then it's going to kind of just go through it, hit it at a point, and then go right through the actual plane. And I know this is hard to visualize. It's almost like saying, take a note card. So if I kind of show you guys here, if you have this note card, this is my plane. And if I have a line, and that's like my pen, instead of the line just sitting on top of the plane, it's like saying it's going to go through it. And it's going to go through it only at this one point. So imagine if I put a dot here, and the pen goes right through it. It's like a hole punch through that. That's the intersection then, just that 1 point. All right, so this would be 1 point. That's one way to imagine the intersection. That's not the only way, because I can also take the plane, here's my plane, P, and I can take a line and just have it kind of increasing, sitting on top of the plane the entire time. That's what I mentioned, like here's my plane, and the pen, which is the line, just kind of sitting on it the entire time, and that's the intersection. Well, if that was the intersection, then the answer here would be infinitely many solutions. Because at every single point on this line, there's a solution. So infinitely many points or solutions. We're going to say points because there's lots of points on here. And they both would increase forever, right? The line, I'm going to say line J, I forgot to label that, would go everywhere left to right, and the planes are also going to be infinite as well. So the planes will always, although we draw them like this, they will be infinite planes. They do increase and decrease in all directions forever. So infinitely many points, and specifically it's going to be the geometric figure that it represents will be a line. So when I say what is the intersection here, it's actually line J. Line J is that intersection. All right, on to the next one, two planes, plane P and plane R. Well, there's lots of different ways to imagine this. Now, of course, the planes could be parallel, and that could be no solution. So I'll write that as an option here in just parentheses. Parallel planes, no solution, or no points. So they would not intersect, but we're kind of looking for an intersection, so I don't want to use that example. But so what if instead I take my plane and I draw, say, plane P here. Okay, and then next I want to draw a plane that's kind of like, say it cuts right here through this line. So I would draw it so that, like, this is harder to do. So anytime the plane comes in contact with it, I usually do dashed lines, little like dotted lines here. And then, so imagine kind of like this. Okay, and then it goes down like this. So imagine that this plane, and so I have to label my plane R, that's the other plane. If the two were intersecting at, and then just kind of met at this line, that's where they cross. The two planes kind of hit each other. It's like saying take two note cards, and then you'd have to make slits in the note cards so that you can kind of go through it. And then that slit that was there would be like the line of intersection. So a line would be, again, the area that they intersect. So this would be infinitely many points again. Oh, I spelled that last one wrong, but we'll look at that again. Infinitely many points. And so again, a line would be the geometric figure that the intersection represents, because infinitely many would have to intersect at a line. There's no label for this line, though, so you would have to give it a name if you were talking about this specific line, if it wasn't labeled for you. I spelled this wrong. Infinitely. There we go. All right, so infinitely many points on that one. Okay, so on to another example, point M and plane P. So point M and plane E is pretty straightforward. You have this plane P, and there's a point somewhere in the plane. That's it. There's really no other way to imagine this. So one point. Now, of course, the point, I guess, could be nowhere in the plane. So again, no solution is possible for a lot of these. I only mentioned it for this one with the parallel planes because I wanted you to be able to think about that. But it is possible for every one of these examples. We are looking for intersections, though, so we don't want to say a no solution. And then infinitely is not possible with that. All right, on to this last one, 2 points. That's pretty easy to see, hopefully. The point right on top of the other point. So say you have M and E right there. Again, no solution is possible if the 2 points are not on top of each other, but we're looking for intersections. All right, so that's pretty much it for the different representations. Let's kind of summarize here. If we have 2 distinct lines intersect, the intersection is a point, like we saw. Let me go back up and show you right here. This example to the right. Because although they can have no solution or infinitely many solutions, we're looking for the 1 point here because it's the most common when the 2 will intersect. And they cross just at 1 point. All right, if 2 distinct planes intersect, the intersection we saw was a line, and whatever that line that would have been, we would have labeled it. Okay, and then same idea, through any 2 points, we've talked about this postulate already, through any 2 points there's exactly 1 line, and through any 3 non-collinear points there's exactly 1 plane. Please make sure you know both of these postulates by now. And then finally, if 2 points are in a plane, then the line that contains them, it also has to be in the plane. Okay, so let's kind of imagine this for a second. You have these 2 points in the plane, so imagine a plane here, 2 points sitting on it, and the line, obviously if it's 2 points, we know 2 points are collinear, so there would be a line that contains them, well then that line has to be in the plane. There's no other way around it. All right, so that's it for the front page so far. If you have questions, just kind of jot them down, star it somewhere, and then bring them tomorrow, and I will go through as many questions as you have from the notes as well as the homework. All right, on to the next page. We're going to do a quick algebra recall. As I've mentioned, we kind of do algebra throughout the year. It relates to what we're doing right now with intersections, because it's saying you have a line and a point, determine whether they're going to intersect. So when we go to substitute them back in, we'll see if the point is actually on the line or not. So this would be 6 equals 4 times 1 plus 2. Make sure you're substituting them in the right spot. The 1 is the x value, the 6 is the y value. And this is a true statement, right? 4 plus 2 is 6, and since 6 equals 6, true, then we would say the point is on the line. Whereas on the next example, if we do this next one and we find out, nope, that doesn't work, if the two sides are not equal to each other, then it won't be on the line. So we have 0 equals, because remember y is 0, negative 2 times negative 4 plus 8. That's positive 8 plus 8, which is 16. Now that's definitely not equal. This is a false statement, and then you would say that the point is not on the line. Okay, so just a couple of quick algebra practice here, just substituting in to be able to determine if there was an intersection there or not. All right, so now we're on to drawing some conclusions based on, it's just a little bit more with planes and points and lines, intersections between them. It says here, use your observations to create these, complete these exercises. We'll do them together though. Explain your reasoning in words or by using a drawing. It says, is it possible for a line and a plane to have exactly one point in common? So we just kind of saw this on the front page, but I'll draw it again. Here's my plane. If the line is not sitting on the plane the whole time, but it's just kind of passing through it, then yes, you have a line kind of dashed here because it's going through it. Here's that point, dash it still through it, something like that. That would be exactly one point that you would get in common. Now exactly 2 points is not possible. That's harder to imagine. There's no way that it could do 2. It's either going to do it infinitely many times or one time, or it could even be no times, right? This would be a possibility. It says no points in common. The best way to imagine that is that the line is just nowhere near the plane. You have a plane and you have a line that's not in it, right? All points in common is possible. It's if you have a plane and the line is inside of it, right? And the plane goes on forever and the line goes on forever. So that's also a yes. And this is like saying infinitely many, like we talked about on the front page. Okay, now number 2 is using those index cards. I didn't pass them out to everyone, but and so I'll go through this real quick and I can show you on Tuesday kind of what this looks like. It says use your index cards to make 3 planes to have one point in common. Is it possible to rearrange them so that they have a line in common? And this is hard to visualize without the picture, so right now I'm just going to write it and I will show you I can show you what it looks like when we play with it. If you deal with it like a pinwheel, then yes, it is possible to rearrange them so that the line would be a common side for the 3 planes rather than just the point, right? We are going to skip number 3. We'll go through more of that if it's going to be on a quiz or a test, but for now, don't worry about that. Number 4, for any 2 distinct lines, how many planes may contain both lines? So we have 2 distinct lines. We have this plane. Imagine something like this. They would have to both be in that one plane. All right, and then number 5, how many points may 3 distinct planes have in common? Well, it's just, again, how you visualize it. You could try holding up 3 note cards and kind of play with it that way. But if I have it where I have one note card or plane like this, and I kind of want them to meet at this point. So I could take the next one, kind of go like that, and then kind of go back like this. And it's hard to draw it, but imagine something like this, where the 3 of them could meet at this line here, and then that would be infinitely many points. And then specifically, I'm going to go ahead and say that they would intersect at a line. So anytime you have like 3 planes, try to imagine how could I do it so that I get the most amount of points there. And you wouldn't just get 1 point, you would get the entire line. All right, number 6, can 2 planes intersect in a segment? And the answer here would be no. And the reason for that is that planes and lines go on forever. And segments have endpoints. They can only do lines or points, and so we've seen how lines are where they have intersections, but not segments. All right, because segments will end, but we need lines to go on forever, because planes and lines will go on forever. And then finally, can 3 lines intersect at exactly 2 points? Well, let's kind of imagine this and draw different ways. There's the one, if you wanted to, they could definitely do 1 if they all 3 go through the same point. Well, and they could do 0 if they don't have any common points here. So 2 is not possible. The 3 lines could not intersect at exactly 2 points. All right, so this is the end of the notes. You have time to get started, hopefully on a homework for at least a little bit of time to maybe get started. It's in your packet. I'll write the page number again here, but you shouldn't really need this. It's page 5 through 8, 14 to 28, 39, 40 to 42, and 46. You don't need to jot this down. Just make sure you know which one. It says 1.A.2 homework. It's that second sheet of paper in the packet. If you don't have the packet, if you misplaced it or something, I do have extras in the honors geometry bin where it says absent. Look here. And that should be it. All right. If you have questions, bring them tomorrow. But hopefully this made some sense for you to at least attempt the homework. All right.